We are taping, as you're seeing, and we will post this online on the internet, in the same site where you registered for the symposium. And so you will then have access to it if you want to review some information. And also, if you want to share it with colleagues who couldn't make it today, there'll be an opportunity to do that as well. Okay. Just tell me when you want to start.
Yep, let me just see this slide.
Professor Israel Wachs, and I do a lot of molecular spectroscopy and catalysis, and so the examples I'm going to show you is applications of molecular spectroscopy for catalysis. I also make use of the XPS instrument, and we published papers with information from that, and I also make use of the laundry ion scattering instrument. And I don't want to belabor that because we're going to get two very beautiful talks like to the world's experts on these latest technologies. So I'm going to talk about optical spectroscopy. And just to put it in perspective, in XPS, you're basically ionizing the material. You're exciting it with X-rays, and electrons are leaving and being analyzed. And in laundry ion scattering, you're bouncing noble gas ions off the surface. Also, even though it's laundry ion scattering, it has quite a bit of energy in the ions. And what I look here is the scale of energy, and so we're not going to look at this kind of ionization for electron spectroscopy. We're going to look at the much lower energies in the ultraviolet region, the visible, and the infrared. And here we're looking at molecular vibrations. Okay? And also in the UV region, we also get electronic information. And so we're operating in this region here. And I'll show you examples of how we use this information. So this slide here shows you kind of characterization techniques that are typically used in catalysis research. And you can see that XPS is up there as well as laundry ion scattering. And here, we have limitation of pressure, unfortunately. And here they tried very, very hard to address this, but it's a real issue. And in the XPS, we can go now to millibar. You heard, typically it's guaranteed like 25 millibars, but they've even gone to 250 millibars, which is a far cry from 10 to the minus 9, 10 to the minus 10 torr. It's a million order of magnitude increase in pressure. The reason I focus on some of these other techniques, in particular the optical techniques, is because of the fact that I can go high pressure, and I'm interested in catalysis, and catalytic processes are high pressure processes. High pressure meaning even 1 atmosphere or even higher. Personally, I don't really go more about 1 atmosphere, but you want techniques that can operate also over a higher temperature region. So I don't think any of the techniques really have a problem with temperature. The pressure is the limit. And one of the things that I like, one advantage besides the pressure issue with optical spectroscopy is that you can get molecular level information. And I'll show you that. Unlike, we don't have, still a resolution problem, but this optical, the wavelengths are much larger, and so you still have problems with getting really good spatial resolution. It's not a TEM, angstrom level resolution, but we're getting molecular level information. And the techniques today have been much faster today, and you can get very quick signals with these techniques. So here's a summary. So I'm going to talk about the two vibrational techniques that are most common: is infrared spectroscopy, Raman spectroscopy, and finally both are looking at vibration. And they're going to look at ultraviolet ultraviolet distal spectroscopy, which looks at electronic changes. So the vibrations, without going into details, but I'll show you a little bit later in the talk, are related to the symmetry of the molecule. So you get really molecular level information. And for infrared, in order for it to be, whatever you're looking at to give a signal, there has to be a change in dipole moment, and IR tends to favor the asymmetric vibrations, and again, I'll elaborate about that later. IR, people, at least in catalysis, in a lot of areas, they think that it's a surface technique, but it is not. It is a bulk technique. The signal goes right through your material. Okay, you have transmission IR. However, if you put a molecule and it happens to stick on the surface, and you're looking at the molecule, what it's doing, it gives you some indirect information, but it's not direct. So in that way, you're converting a bulk technique to give you some sort of extracting surface information. Okay? And IR is very good at looking at hydroxyls because of a very large dipole moment. It also absorbs molecules and surface intermediates. And the combination of molecular information, vibrations, with the ability to operate at higher temperature and pressures makes this a very versatile technique to complement other techniques. This is sort of a layout of a typical IR spectrometer. So you have the IR source and the beam splitter, and it goes right through your sample. You can also have diffuse reflectance IR and bounce it back and analyze it if you have an opaque sample. But you can also go right through the sample, then it goes to your IR detector. And what you're looking for is the vibrations of the material. So here, for example, I'm showing you some examples from work that we've done in our laboratory. This is one thing that I mentioned earlier, that the hydroxyls have very large dipole moment, and you can see OHs. And if you look at this is alumina, this plain, I mean, it's a gamma alumina kind of material. So there's a lot of OHs. And here are the various assignments. So not only can you see the OH, but you can see the different OHs. And if you put on a molecule on the surface, you can see which OHs are being reacted. And they have different chemistry. This one is more acidic, basic, and this one's more acidic. And so you can see where things are going. And this has on the surface, and this has consequences for the surface chemistry. Just to give you an example, here's I'm absorbing formic acid at 100 degrees C, and as a function of pressure. And initially, you get these vibrations here, which are related to this dark labeled band, and this is this structure here. And this is a bidentate, so the formic acid breaks an OH bond, and it goes up, it absorbs with two oxygens bonded down to the site. But as we put more, increase the pressure of formic acid, we get these other bands here that are red, and these are the monodentate, so the surface becomes more crowded, and it's not possible for the formate to put both oxygens down, so it makes this structure. And if you keep putting more pressure, you get these blue bands here, and this is just formic acid that's sitting there, it's physically absorbed. It's a very small amount, but it means that you've saturated the surface, that you've gone beyond the monolayer of formates on the surface. So this is what I mean by molecular spectroscopy. That, I mean, we're starting with formic acid, but we have three kinds of formic acid derivatives on the surface. Another trick that people do is they're interested in the acidity of surfaces. And so on the surfaces can have loose acid sites, you can have Bronsted acid sites. Bronsted acid sites donate protons. And so what they do is they absorb a basic molecule. In this case, it's pyridine. And this is the IR spectrum for pyridine on this aluminum oxide aluminum catalyst. And L is for Lewis acid. And so the pyridine is just pyridine on a Lewis acid. But on the Bronsted side, these are pyridine, it's actually pyridinium ion. It's actually picked up a proton. And that shows you that you have Bronsted acid. If I took away the molybdenum oxide and I repeated this experiment, you see no Bronsted acid sites. So that Bronsted acid sites were created by the addition of aluminum oxide to the surface. And so many people, especially if you're interested in acid catalyzed reactions, are interested in this kind of fundamental molecular information. And one of the drawbacks of infrared, because of the strong dipole moment of OH, the IR absorption is taken by water, so you cannot look at liquids. Water, aqueous water. However, there's a trick to play, and it's ATR-IR, and it turns out that if you have the right angle and these single crystals, and whatever you're looking at in the liquid, it's up here. So you have a single crystal here. And if the angle of incidence is greater than the critical angle of the material, the light is completely reflected. And if you took high school physics, when I was a student, I had to calculate the angles, the different materials, so you can do this. It turns out, however, which I was not taught in physics as an undergraduate, as a high school student, is that there's a little bit of this IR radiation that actually goes into the liquid phase. And it's called evanescent wave. Okay? And so what you do is you bounce this many, many times off this single crystal, this infrared, and each time it picks up a little bit of the vibration in the liquid phase. And you can actually start getting vibrations of the liquid phase. So if you're working with materials in the liquid phase, so here's an example where I take TiO2 and I expose it to hydrogen peroxide and water. Okay? And initially you see this band here, and this is the OO vibration of hydrogen peroxide. So this is dissolved hydrogen peroxide in the liquid phase. But notice as a function of time I have a second band growing here, and this is TiOOH. Okay? So you can tell the difference between hydrogen peroxide swimming in the liquid phase and that is bonded to the titanium. And also there's a little peak here. It's a very small amount. It's a superoxide. So some of this is decomposed by losing the hydrogen and it's made O2. So it's still molecular, but it now has a negative charge on it, and that vibrates over there. Again, this is the strength of molecular spectroscopy. If you change something, so you have here three kinds of species. You have the aqueous the aqueous hydrogen peroxide. You have titanium peroxide, and you have the superoxide. So titanium superoxide. So there are three kinds of species. Two on the surface and one in the liquid phase that it's coming from. So you can study absorption from the liquid phase. Okay, so that's a quick summary, just to give you a flavor of what you can do with with infrared, any kind of information. Now I'm going to show you Raman spectroscopy. Raman and IR are sort of mirror images of each other. They're very related. And again, the vibrations are related to the symmetry of the molecule. The selection rules for Raman are slightly different, in that you see a band, there's a change in electron polarizability when the light comes in contact with it. And consequently, you go through selection rules, the Raman favors symmetric vibrations, where IR favors asymmetric vibrations. And together, that's very, very powerful if you can do both. So again, Raman is a bulk technique, okay? It doesn't just look at the monolayer, but if you have something that's on the surface, and if it is able to give a good Raman signal, then you can follow things on the surface. Okay? And it's particularly good for double bonds or triple bonds, whether they're oxides or carbon-carbon bonds, because they have a high electron density, they have a large change in polarizability when the photons come in contact with this bond. And if you have a crystal of a metal oxide, it's going to give a very sharp, stronger bands that ban something that's amorphous, disordered on the surface. And again, it has molecular nature because of this, it's related to the symmetry of the molecule, and it can operate high temperature and pressures. And also, unlike basically what IR can't do, Raman can do, and vice versa. So IR has trouble with water because of polarizability issues. Raman doesn't care about polarizability, and you can do it through water. Okay? So this was discovered by Sir C.V. Raman in 1928. I think he got the Nobel Prize a year until the advent of the laser in the 60s, the signal was very, very weak using mercury arc lamps and stuff like that. Just to show you, so the difference is in infrared, you're absorbing the photons from going from the ground state to some excited state. In Raman spectroscopy, there are three processes. You absorb the photon, and it's excited to a higher vibrational state, and then it comes down. And if it comes down to the ground state again, we call that Rayleigh scattering. And most events are this. And basically you get no information because you ended up where you started with. If, however, it comes back down to a higher level, then the difference, then from this you're going to get Raman bands, from the new Raman bands. And this is referred to as Stokes. If it goes to a lower level, then an initial start is called anti-Stokes. And these bands, usually people doing Raman are looking at the Stokes. The signals tend to be stronger than the anti-Stokes. So it's very rare that anybody publishes. People do publish anti-Stokes and compare the two. You can actually tell the temperature of a sample. There's a formula that allows you to do that. But generally, the instruments in the past have been Stokes Raman. So this is a schematic of this instrument. Basically, the key here is the monochromatic, high energy, well, focused, laser. And so you hit whatever the sample is, and it goes down, then it's bounced back into our system. We have a filter. This is a big development in the 1990s to knock out the Rayleigh scattering, because the elastically scattered has no information, but is a huge light signal, like 99.9% of the signal that comes back. And really you're looking for 0.1%. So this cleans that up, and the residual that's left, that the actual inelastically scattered, so they exchange energy and vibrations with the material, is then put on this dispersion grating and then goes onto the charge coupled device detector, which simultaneously sees all the vibrations from about 0, it depends on how your instrument is designed, from 0 to 4,000. Typically people are looking at like 100 to 4,000. And so this is qualitatively. So this here, I'm showing you molybdenum oxide in water. So just to show you that we can look in water. And so if you're making a material with molybdenum oxide and preparing it, and you want to know how it changes. So all we're doing here is change the pH. And you can see that the vibrations are changing. At the highest pH, the 173 band is the glass plate that we're using to put the drop on. We can't levitate the water drop yet. So that's nothing. But you can see here, you have these bands here. At this pH, what you have is isolated MO4 structures. And these vibrations, the symmetric, asymmetric, and this is the bending modes of MO4. And notice as I lower the pH, this band goes away, and some other bands are coming up, and these bands are shifting. So at pH 6.16, what you have here is, this is heptamolybdate. It's a cluster of 7 molybdenum oxides. I think it's MO7024 cluster. And notice as I keep lowering the pH, making it even more acidic, the bands shift again, and now the band's at 965. This is octamolybdate, so it's a cluster of 8 molybdenum. And again, what I'm emphasizing is the molecular structure of this, that I can tell just by the vibrations, not only in this position, but all these vibrations, what we're looking at, what kind of species we're looking at. And in this case, you can't, you're hard pressed to do this with IR. I've not tried this with IR, but with conventional IR, you cannot do this with Raman. It's very straightforward. Another thing that you can do is look at phases of materials. So phases are different phases of a material. So it's still, in this case, iron oxide, but different phases, the atoms are arranged differently, and consequently they vibrate differently. And since they vibrate differently, you're going to get different spectra. And so here is FeO, is +2. This is Fe2O3, you get these vibrations, and you can see again, I told you, sharp bands, and this is +3 iron, and Fe3O4 is a combination of +2 and +3, and it only has this band here. So just by looking at the Raman spectra, it's not only if somebody has iron oxide, what kind of iron oxide? Do you have one? Do you have all three there? You'll be able to tell. I'll show you that in a minute. So here's an example of an iron oxide catalyst. This is actually a commercial type catalyst. What it is, it's a mixture of iron oxide and chromium oxide. And this catalyst makes hydrogen. It's used in industry to make hydrogens. The reaction is called water-gas shift reaction. It reacts water with carbon monoxide, and the products are CO2 and hydrogen. And that's how industry makes hydrogen. And if in the next year or two, more in California than here, but in LA, but they're just putting in fuel stations for hydrogen cars that Toyota and Honda are coming out with, and they're going to use this technology, this catalyst, to make a hydrogen for fuel cells. Fuel cells for operating the cars. Anyway, so here is the Fe2O3 phase, which I showed you before. It's a very nice series of bands. And in here, I made the catalyst, and for example, here's chromium and iron. And you see now there are new bands. There's a little shoulder there, and you see also this band here, H44, and you see this band at 1003. Turns out the 1003 band is due to this, it's chromium +6. I'll show you more information of why this is the structure. And this vibration here, so this is, what we're looking at here is this vibration of this guy. H44 is the chromium bonded to the iron, and this new band at 664 is chromium +3 dissolved in the iron. So you have three different, well, it's two different chromium materials. And here we've added copper, but it doesn't really change the Raman spectrum, only a small amount of copper. But look what happens now. This is now during a reaction, which I believe is 400 C. Okay? And now everything's changed. Okay? And this is why it was referred to earlier by Henrik about the need to expose things to a reactive environment that it can change. And so the Fe2O3 phase now has become Fe3O4. These vibrations are Fe3O4. It's totally changed. And notice that the chromium vibrations are now gone, which means that the chromium-6, the chromium is there, but it's just not +6 anymore. It's a reduced state. And it's actually, a lot of it has gone into the iron. Yeah, that's why it's left the surface. It's dissolved into the iron. So, quick comment about vibrations and symmetry of molecules. So this is what a dioxyl molybdenum oxide. So this molybdenum oxide is 4-coordinated. It has 2 double bonds sticking out, referred to as oxyl bonds, and it has 2 bonds to the surface, which happens to be silica in this schematic here. And the symmetric stretch is when both of these are vibrating in sync. Okay? And that occurs in 983 wave numbers. The asymmetric stretch occurs, both one is going out and one is going in. The vibrations of the oxyl bonds, and they're out of phase. Okay? And this asymmetric vibration is 968. And this is the bending mode, and this the angle between oxygen molecule and oxygen is changed. Okay? And so you have 3 vibrations if you have this structure, and certainly the symmetric and asymmetric. If you only have, if the molybdenum oxide has 1 double bond and has 4 bonds anchoring to the silica as shown here in the schematic, the only thing the oxygen can do is vibrate up and down. So it cannot have an asymmetric. It only has a symmetric. So in this case, there's only 1 band, and here there are 2 bands. And so I'll show you how we use this to tell the molecular structure. So here is the Raman NIR. And so here I have the Raman for this chromium on iron oxide. This is before exposing it to the reaction. The vibration is around 998 by 1,000. And notice here, the IR is at 1010. And remember, Raman is sensitive to symmetric, more sensitive. And so it's very weak here. It's there, but it's very weak. It's the shoulder. The IR sensitive to asymmetric. So you have it the shoulder and the Raman. And so that's how we know the structure of the chromium +6. And we can do XPS to also show that it's +6. And in fact, we've done XPS, and we know that after the reaction, it's +3 when it goes into the material. So the last technique is ultraviolet visible. So unlike the vibrational spectroscopy, the ultraviolet visible allows me to detect electronic transitions. And this has to do with oxygen to metal charge transfer of bands. And I can tell from this how big is whatever I'm looking at. Is it a monomer, a dimer, a polymer, a cluster, or a particle? And also I get some coordination information. Particularly I can get the domain size and gives information about the dispersion. So also, if you have reduced cations, you get what's known as DD transitions, and you can see that the environment that you put in the material might reduce, and you'll see that. So this technique is quantitative, but only low concentrations, like less than 1%. It gets to be nonlinear higher concentrations if you want to do quantitative analysis. So basically, the way traditional UV vis works is here's your light that's coming in, your light source, and here's your sample, and it's bounced all over the place, and you have this collection sphere, and this is your detector. So this is a white sphere, so it doesn't add any UV vis transitions, but it causes more bouncing of light into your detector to enhance your signal. Okay. Recently, so there have been companies coming along with optical fibers, and what it is that this center point is where the laser light is coming from, the UV vis light is coming, and these around here are the collectors, and they send signal to the detector. And the unique thing about this, conventional UV vis takes about 15 minutes. The quality is very, very good, very high quality. This can take milliseconds, but it's a lot noisier. But it has to go through fiber optics. And so here's some examples of UV vis. And so here's a material, it's +5 vanadium, and this is this charge transfer band. And notice that this is +4, and this is +3 that is moving with the oxidation state to higher and lower nanometers, small wavelengths, higher energy. Okay. Notice also that the +5 has no DD transitions. There are no reduced cations. Once you go to +4 or +3, you start getting these secondary bands. They're weak. They're much weaker than the charge transfer band, which dominates. But nevertheless, you can tell by their positions that you're getting, under your conditions, reduced states. And the other nice thing is that you can determine how big something is. So for example, if I'm looking at vanadium material, and you can do this for other oxides, and I can be a monomer, I can be a dimer, where you have a VOV, virgin bond, or I can have a chain or a polymer, or I can have also a cluster, up here. And what happens is that as the material, the number of vanadium sites in your basic unit, your nano particle, let's call it, increases, the edge energy goes down. And this is plotted as a function of the number of bridging VOV bonds. And the reason is that what we're measuring here is the gap. It's the optical band gap. It's the gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. Okay. And as the material gets more and more VOV bonds, the electrons can be distributed on more than just on the site that they're on. They're not localized. As they become more delocalized, the band gap goes down. And so you can tell, if you have an unknown material, you can just measure the band gap and you can see if it's a polymer, a dimer, a monomer, or a cluster. And here is the actual spectra. So this is for this structure here is isolated, and this structure here has a pair, it's a dimer, has the VOV bridge here, and this is a sheet of this structure consists of sheets. You see the edge-edged sheets are changing. This is going towards the visible. So you can tell the size of something. Unfortunately, not all materials do give very nice viewed signals, but there are quite a few materials that do, and so you can learn about oxidation states, and you can learn about dimensions we call domain size. To the end, so what we've done is we've built this is a Raman spectrometer module from Horiba, and they make an instrument called LabRAM IR. So they combine Raman and infrared. It's a high-resolution system. This is the platform. This is our samples, and we can run reactions and we can expose this to different environments. And you'll have also a microscope here. So you can do, if you really optimize the new system, you can do like 400 nanometers resolution. There's now people talking on tip-enhanced Raman. They're talking about a few nanometers, but it's very exotic and it's just happening. But we don't have that here yet. So, but the signals, the optical lights come through here, and they bounce back into the microscope and then go back to our detectors. So just drawn to the schematic. So we have the CCC detector, which allows us to do to collect the Raman spectra, which is indicated here. We can do the same with the IR detector, and we also have fiber optics UV vis. So we can combine 3 optical spectroscopy methods on one material. We also have a mass spec and GCs to analyze the products, so we can see what is being formed. This allows us to relate what structures we see with the catalytic performance. And what I'm trying to do, and we're going to submit a proposal in the next few months. The National Science Foundation has a call for proposals for new instruments. It's called Major Research Instrumentation. And what I'd like to do is take the Sienta, or the VG Sienta latest model, the R4000 HIP 3, which can do the ambient pressure measurements, and connect and hook it up with optical spectroscopy, so that we can, at the same time, while we're measuring XPS, ambient pressure XPS, we can also, and it has a residual gas analyzer, so you can see what products you're making, but also get molecular level information about the structures are there during different environments. Now I'm talking about catalysis, but your applications doesn't have to be catalysis. It can be liquid phase for something, or it could be just, let's say you're a glass person or with ceramics, you just want to see what happens at high temperatures. But at the end of the day, all these techniques together, XPS, LICE, and these optical techniques, and also you'll hear, we'll talk after me about AFM, are all needed to really understand your material. So thank you for your attention. I'd be happy to answer the questions you have.
Any questions?
So, Israel, FTIR band assignment is relatively straightforward because you can do it with quantum chemistry easily. Now, UV-Vis band assignment is not, I mean, it's difficult to model. I mean, excited states are difficult to model accurately with the EFT. So what do you rely on when you assign your UV, so those broad band assignments? What do you rely on?
Well, you saw in the example I showed the vanadium and it had plus. So you knew the compound. You have to have a reference compound. You know I'm dealing with +5, +4, +3. So you can see where the charge transfer bands occur. You can see where the UV transition occur. As far as calculating the domain size, again, we have to establish this curve by measuring reference compounds with known structures, and that's how we're able to do that. So I guess the answer to your question, experimentally, we've been doing it, but with modeled reference compounds where we know the structure. Okay, so if no further questions, then thank you again. And the next speaker is going to be Jonas Baltrusitis. So I can't pronounce his name, so I'll introduce him.